All right, today we are going to be talking about commonly used negative feedback amplifier configurations. So let me write that down. And we are largely going to use the three-step process that I introduced to you guys in the last video in order to develop these relationships. So let's look at circuit number one. And after we analyze it, we will give it a name as well. So in the first OpAmp circuit, I'm going to start with my OpAmp, put it here. I'm going to put the inverting input terminal on top, the non-inverting input terminal here on bottom, and my output terminal over here to the right. I am going to include a feedback path from my inverting input terminal to my output terminal, like so. And I'm going to call this feedback resistance R2. I'm going to place another resistor connected to our inverting input terminal. Let's call this guy R1. And I'm going to ground the left leg of this resistor R1. And I'm going to apply my input voltage directly to the non-inverting input pin, like so. So this will be Vin. I'm going to measure my output voltage directly at the output node of the OpAmp. Okay, so our first step in analyzing practically every negative feedback OpAmp circuit is to apply OpAmp rule number one, which says that no current can flow into or out of the input terminals of our OpAmp, which means we'll have no current flowing into the inverting input terminal and no current flowing into the non-inverting input terminal. And then using this relationship, we are trying to find what our voltage is at our non-inverting input terminal, right? So this is a nodal voltage here. I'm going to label it. So this is measured with respect to ground. And hopefully by inspection, we can see that that voltage V plus is simply going to be Vin. Our next step is to apply OpAmp rule number two, which says there can be no potential difference at our input terminals, which means that this voltage here, which I'll call V minus, is also a nodal voltage, meaning that it's measured with respect to ground. Since there can be no potential difference between the input terminals, since V plus was equal to Vn, V minus must also be equal to Vn. And now we are going to apply Kirchhoff's current law at the non-inverting input node. So I'm going to be adding this current and this current together, setting them equal to 0, and this should allow me to solve for the quantity V out that we're interested in. So my KCL equation is going to look like V minus divided by R1 plus V minus minus V out divided by R2 is equal to 0. Substituting in that V minus is equal to Vn, and moving things around a little bit, we're going to have Vn times a factor of 1 over R1 plus 1 over R2 will be equal to V out over R2. And then we can simply multiply both sides by R2, giving us the relationship V out is equal to 1 plus R2 over R1 times Vn. So anytime we have this particular configuration, then we no longer actually need to analyze the circuit at all. It will always behave using this particular relationship. Okay. So let's make some observations about this relationship. Okay. The first observation that I'm going to make is about what's called the voltage gain of the circuit. So the voltage gain, A subscript V, is defined to be the ratio of the output voltage divided by the input voltage, which in this case is simply the quantity in brackets 1 plus R2 over R1. So the voltage gain is defined entirely by the resistors that we use to bias this OpAmp circuit. So if we look at this expression, we can see that if we have a positive input voltage, we will get a positive output. So effectively the quantity 1 plus R2 over R1 will always be positive. So that's one of the reasons why this amplifier is called a non-inverting amplifier circuit. So the output signal will have the same polarity as the input signal. Another reason why it's called a non-inverting amplifier is because the input signal is applied at the non-inverting input pin. Okay. So our voltage gain can never be negative, but it can also never be less than 1, right? The smallest possible value that our voltage gain could have would be something very close to 1, where R2 was effectively a short circuit and R1 is effectively an open circuit. Okay. So this particular amplifier is used strictly to boost the level of an input signal, right? So if we put 2 volts in and we configure our resistors correctly, we could get 5 volts out or something like that. The second circuit that we're going to look at is almost identical to this non-inverting amplifier topology. The principal difference is that we are going to swap where we apply ground and where we apply our input voltage. Let's put it down here. So this will be circuit number 2. Once again, the inverting input terminal will be on top. The non-inverting input terminal will be on bottom, although there are ways to draw it with that configuration changed. My output pin is going to be over here on the right. I'm going to have a negative feedback path connecting my inverting input to my output, like so. So once again, let's call this resistor R2. I'm going to have a resistor R1 also connected to my inverting input pin. And now I'm going to apply my input voltage here at the left leg of resistor R1 instead of ground like I did in the previous circuit. And I'm going to apply ground here at the non-inverting input pin, which is where I applied VN last time, right? So these circuits are identical, except that we've simply swapped where ground and VN are applied. So starting our analysis now, we know that no current can flow into the input terminals. And we can see by inspection that the voltage present at the non-inverting input terminal is 0 volts. Applying op-amp rule number 2, the voltage present at the inverting input terminal must also be 0 volts. And now we're going to apply Kirchhoff's current law. So we're going to add this current and this current together. And so that's going to look like V minus Vn divided by R1 plus V minus V out divided by R2 is equal to 0. Now we're going to substitute in that V minus is equal to 0. And so that's going to give us negative Vn divided by R1. Moving our output voltage to the right-hand side is going to give us V out divided by R2. And now with a trivial amount of math, simply multiplying through by R2, we find that our output voltage V out is negative R2 divided by R1 times Vn. The voltage gain for this circuit, again, simply the ratio of the output voltage to the input voltage will be negative R2 over R1, which means that if we apply a positive signal at the input, we will get a negative signal at the output. So we are inverting the polarity of our signal. So this is an inverting amplifier. Another way to think about why this is an inverting amplifier is because the input signal is applied through a resistor network to the inverting input pin of this amplifier. Okay, so the the inverting amplifier that we see here is a little bit more versatile than the non-inverting amplifier that we dealt with previously. So what I mean by that is this inverting amplifier is capable of boosting signals. If R2 is greater than R1, then the output signal would be greater in magnitude than the input signal. But it can also be used to attenuate signals or make them smaller, right? So if R2 is smaller than R1, then our voltage gain will be less than 1, which means our output voltage will be smaller than our input voltage. This versatility comes at the drawback, so to speak, of having an output signal that is of the opposite polarity of our input signal. This really isn't much of a drawback whatsoever, particularly when we're dealing with oscillating circuits and things like that. Just means that we have a phase shift, which we'll talk about more later on. So this inverting amplifier configuration is actually the most widely used op-amp configuration. And in fact, several of the other configurations that we're going to talk about today are based on this configuration. So let's look at the first one of those right now. So this will be circuit number 3. I'm going to start with my OpAmp down here. Inverting terminal, non-inverting terminal as per usual. Output node here. I'm going to have a feedback path. I'm going to call this resistor RF this time, and you'll see why in a moment. And what I'm going to do now is I'm going to apply multiple resistors to the inverting input terminal. So let's call this one R1. This one R2. And this one R3. And then I'm going to apply my input voltages. So V1 will be an input voltage. V2 will be an input voltage. And V3 will be an input voltage. And I'm going to ground my non-inverting input terminal and measure my output directly at the output terminal. So starting our analysis, we know that the currents flowing into our input terminals must be 0. So we can see by inspection that the voltage present at the non-inverting input terminal is 0 volts. Applying OpAmp rule number 2, the voltage present at the inverting input terminal must also be 0 volts, since there can be no potential difference. And now I'm going to apply KCL. So I'm going to have this current flowing out, this current flowing out, this current flowing out, and this current flowing out. You can add them all together. So that's going to look like V minus V1 divided by R1 plus V minus V2 divided by R2 plus V minus V3 divided by R3 plus V minus V out divided by RF is equal to 0. Substituting in that V minus is equal to 0 volts and moving V out to the right hand side of the equal sign, what we're going to wind up having is negative V1 over R1 plus V2 over R2 plus V3 over R3 is equal to V out over RF. And then simply multiplying through by RF, we can see that our output voltage is negative RF times V1 over R1 plus V2 over R2 plus V3 over R3. This is the most simplified form. I'm going to expand this out a little bit. We'd have negative RF over R1 times V1 minus RF over R2. Sorry, my stylus not writing the number 2 well. Oh, that's not supposed to be a 2, that's supposed to be an F. My apologies. Times V2 minus RF over R3 times V3. I've put the output voltage expressed as this combination of signals because it makes it a little bit more obvious as to what's happening here, okay? So each one of our input signals, V1, V2, and V3, are being scaled by an individual gain factor that is established by the feedback resistance RF and the resistance placed between the non-inverting input terminal and the input signal of interest, right? So each of those input signals is being scaled or weighted by a different amount, and then the result is added together. So this is what's known, I'll put the name down here, as a weighted inverting summer. Weighted because each individual's input signal is scaled by a different amount. Inverting because the polarity of the input output signal is opposite that of the input signal, and summer because it is effectively adding these inputs together. In a special case, so let's put it down here, if R1 is equal to R2 is equal to R3, we'll just call this R. Our output relationship simplifies to negative RF divided by R times V1 plus V2 plus V3. So since all of the input signals are scaled by the same amount, we no longer have a weighted inverting summer, we simply have an inverting summer. So this is how the mathematical operation of addition can be applied to signals. Okay. So the next one that we're going to look at is going to give us subtraction of signals. Okay. So starting with our op-amp here. Inverting input, non-inverting input, and output. We're going to have our negative feedback resistor connecting the inverting input terminal to the output. Let's call this resistor R. Then we're also going to have an identical resistor R placed between the inverting input terminal and our input signal, which I'm going to call V1. And then over here on the non-inverting side of the circuit, we are going to place a third resistor R between the non-inverting input terminal and ground. We're going to have a fourth resistor R connected to the non-inverting input terminal, and we're going to put our input voltage V2 on the left leg of that last resistor R. And finally, we're going to measure our output voltage directly at the output pin of the op-amp. So for analysis, step one, the currents flowing into the input terminals must be 0. So now we need to figure out what this voltage V plus is. Okay. So this is the first one that we really can't tell what it is by inspection, but we can, or at least not simple inspection. So what I'm going to do is I'm going to effectively follow a current, right? So if V2 is greater than 0, we should see some amount of current flow through that horizontally oriented resistor R. None of it can branch off and flow to the right because that would be flowing into the non-inverting input terminal. So all of that current must be flowing down through the vertically oriented resistor R, which means that these two resistors effectively appear as if they are in series. Okay. So we have what is commonly known as a simple voltage divider at the non-inverting input of this circuit. Using voltage division, our voltage V plus is simply going to be 1/2 of V2, because if the resistors are identical, half of the voltage drop of V2 will occur across the horizontally oriented resistor R, and the other half will occur across the vertically oriented resistor R. Applying OpAmp rule number 2, we know that V minus must also be 1/2 of V2. And now we're going to apply Kirchhoff's current law, adding these two currents together and setting them equal to 0. So that's going to look like V minus minus V1 divided by R plus V minus minus V out divided by R is equal to 0. And I'm going to effectively multiply through by R, which will get rid of those guys. And then I'm going to substitute in my value for V minus, right? So I'm going to have 1/2 of V2 minus V1 plus 1/2 of V2 is equal to V out by moving V out to the right hand side of the equal sign. And now I'm going to combine like terms, excuse me, giving me the relationship that V out will be equal to simply V2 minus V1. So this is what's known as a differencing amplifier. And it is how the mathematical operation of subtraction is applied to analog signals. Now, if we chose to use different values for each of the resistors, we would wind up weighting the input signals by different amounts. And so we wouldn't have, well, we would still get subtraction, but we wouldn't have this simple output result. That being said, the math involved there is not difficult, but tedious. So if we ever wanted to scale our signals differently before subtracting them, it would probably be better to do that using a separate either inverting or non-inverting amplifier stage to get them to establish the scaling factors, and then cascade the output of those stages into the input of the differencing amplifier, as opposed to trying to getting it all done with a single op-amp, which is just, the math is just very, very tedious to figure out how it'll all work out. All right, so just to recap what we've talked about thus far, we have analyzed the non-inverting amplifier and seen that we can boost signal levels or amplify things. We have analyzed an inverting amplifier, which allows us to boost signals and attenuate signals at the expense of having an output that is of the opposite polarity as the input. We looked at the weighted inverting summer, which allows us to add analog signals together. We've looked at the differencing amplifier, which allows us to subtract analog signals from each other. Multiplication and division cannot be done using simple op-amp circuits like we're dealing with in this class. However, differentiation and integration can. So those are the next two circuits that we're going to look at. So circuit number 5 is effectively an inverting amplifier, but we're going to replace one of our resistors with a capacitor. We can also do this with an inductor, but in practice, capacitors have better tolerance values than inductors do. So generally speaking, you would make your integrator and differentiator circuits using capacitors most likely. So let's see here. Here we have our simple op-amp. I am going to put a resistor here in the feedback path, like so. I'm going to place a capacitor here. And here's where I'm going to apply my input signal. And this is going to be a time varying input signal now. So Vn of t. And I'm going to ground my non-inverting input terminal and measure my time varying output signal V out of t over here directly at the output terminal. Okay. So before we get into the analysis like we've been doing, I'm simply going to make a couple of quick notes here. So the first thing that I'm going to do is I'm going to choose the polarity of my capacitor voltage Vc of t such that the positive polarity is on the left. Similarly, I'm going to call the current flowing into the positive polarity terminal of my capacitor current IC of t. And just to remind us of the relationships that we've learned previously, we should know that IC of t is equal to C dV by dt. Or we could go the other way around and say that Vc of t is equal to 1 over C times the integral from negative infinity to t of IC of t prime dt prime. Those are just the current voltage relationships for capacitors that we discussed in class about 2 weeks ago at this point. So now let's get into the analysis of our circuit. So as per usual, we will observe that no current can flow into the input terminals of our op-amp. We can see by inspection that our voltage V plus, the voltage present at our non-inverting input terminal is 0 volts, which means the voltage present at our inverting input terminal must also be 0 volts. And now we are going to apply Kirchhoff's current law at our inverting input node. I'm going to do this ever so slightly differently. I'm going to say that this current flowing in will be equal to this current flowing out, right? Well, the current flowing into that node is just IC is going to be 0 minus V out. So I'm just going to call this negative V out divided by RF. So what I need to do now is figure out how IC of T relates to our input voltage. Okay? So I'm going to use this relationship here and substitute in that C times the derivative of my capacitor voltage with respect to time will be equal to negative my output voltage divided by my feedback resistance. So I at least have things in terms of voltage, but now I need to figure out what the relationship between VC and VN is. Okay. So if I look here, do this in pink, the positive polarity terminal of VC and the positive polarity terminal of VN are shared at this pink node. Okay. The negative polarity terminal of VN is at ground or 0 volts, and the negative polarity terminal of VC is also at 0 volts. So that means that VC and VN are literally the exact same voltage. So let me write that here. VC of T will be absolutely the same as Vn of T. Using this relationship and rearranging slightly, V out of T will be negative RF times C times the derivative of my input voltage with respect to times. So this particular topology is what's commonly referred to as a differentiating amplifier. Because the output signal is a scaled version of the derivative of the input signal. This particular amplifier can also be used without making any adjustments whatsoever as a low-pass filter circuit, which we won't talk about in this class in particular, but we'll talk about in later electrical engineering classes. It's also a fundamental building block of control schemes as well. So this is very, very good to understand how it behaves. To get the integrating amplifier, we are simply going to swap the positions of our capacitor and our resistor. Okay. So our last circuit for today will be circuit number 6. Starting with my OpAmp here. I'm going to place my capacitor CF in my negative feedback position. I'm going to place a resistor R here. We'll apply my input signal at the exact same node. So this is Vin. I'll ground this here and we'll measure V out here. And once again, I'm going to explicitly say that my capacitor voltage will have positive polarity terminal on the left, and my capacitor current, IC of T, will flow into the positive polarity terminal. So for our analysis, currents flowing into the input terminals must be 0 amps. By inspection, the voltage present at the non-inverting input terminal is 0 volts. So the voltage present at the inverting input terminal must also be 0 volts. And current flowing into the inverting input terminal must be the same as the current flowing out of the inverting input terminal. So that means that we are going to have V in minus 0 divided by R will be equal to IC of T. So now we've got to figure out how IC is related to our output voltage, right? So let's look at some things here really quickly. Our output voltage is a nodal voltage, meaning that it is measured with respect to ground. So another way to think about it would be like so. So our positive polarity terminal of the output voltage is at the same node as the negative polarity terminal of our capacitor voltage. The negative polarity terminal of our output voltage is at ground, and the positive polarity terminal of our capacitor voltage is at ground. So from this, we can see that VC is equal to negative V out. Okay. So V out is then simply negative VC, and using this relationship, that means we're going to have negative 1 over C times the integral from negative infinity to T of IC T prime dt prime. Well, we know what IC is. So pulling out the factor of R, sorry, this should be C sub F, we're going to have negative 1 over R times CF times integral from negative infinity to T of Vn T prime dt prime. So our output signal in this case is a scaled version of the integral of our input signal, which is why this is an integrating amplifier. All right, so those are the 6 different types of op-amp circuits that I wanted to introduce to you all today. So if you have any questions about them, please let me know. And if not, I hope you have a good day and good luck on your exam if you have not yet taken it.
On the note of not taking exams, there's no op amps on the final, yes? And on this test.
Okay, so you are correct. There are no op amps on exam number 2. Exam number 2 only covers Thevenin and Norton equivalent circuits, inductors, capacitors, and transient analysis of first order circuits. Op amps will be the first topic covered on exam number 3.
All right, thanks.
No problem.